So, as I mentioned on here, you want to know how to graph these and kind of get the general sense of what these graphs look like. So, in the future, you kind of know what types of vertical asymptotes they might have that might create your limits to not exist. So all this is just going back to limits. So if we know these things pop up whenever you divide by 0, if you just take the denominator and say, well, when is that equal to 0, you'll pretty much be figuring out, if there's going to be vertical asymptotes called VAs, right? And if you know that, you can ask yourself, well, if I know that much, I can probably figure out what happens if I take the limit as we go to that value, right? And you can see if I'm going from the left side, that limit from the negative, right? From here, you can see it will be going to negative infinity, right? And of course, if that's different from the other side, coming from the positive side, right, going to positive infinity, therefore the limit does not exist because these are going to two different values. One's negative, one's positive infinity. So that's what we looked at last week, is that we have to examine from both sides of any given number. If they happen to be the same, then we still have the limit. And if not, then we don't. Right? And so this is what's called a rational function. Just means rational ratio, or just think of a fraction if you have variables in the denominator. Right? That's a rational function. We start having a lot of vertical asymptotes, and you spent probably a good 2.5, 3 weeks on doing these in Algebra 2. And we'll look at a few more of these at the end, right? So definitely don't have any limits here. It's discontinuous, right? And then we looked at these other ones, these piecewise functions, where they kind of jump, right? So here we got, 2, open circle, horizontal, and then x from 0, 0, negative 1, 1, negative 2, 2. Right? So we have here, we have a jump discontinuity, right? And kind of the same, but a little bit different. If we're going this direction, it's approaching 0, right? So from right here, it's approaching the y value of 0. But if you're coming from the right side, it's approaching 2. So once again, they're approaching, 0 or 2 or negative infinity, positive infinity. And once again, because of that, there's two different values. We have no limit. It does not exist. So they have to be approaching the same value. So the discontinuity really helps us. If you can identify that it exists, you can pretty much assume almost always that, okay, here's what kind of limit I'm going to have. All right. Now these are the two we dealt with the most. There's also the third kind that we looked at carefully, and that was when you have variables in the top and bottom, it's important that you attempt to factor. All right? If you attempt to factor the top and bottom, you might find that something, right, cancels out. So here we do have x minus 1 canceling out. So that's why if you graph this, it just appears to be y equals x. Just a nice straight line going through there. So if you put that in decimals, that's probably what showed up. So, but here's one of the shortcomings, right? So if we go back here, let me pull this up here and type this in, x squared minus x. Just type that in. And x minus 1, right? That's why it appears just to be a nice, y equals x, or just, goes through 1, 1, 2, 2, 3, 3. The y and the x are the same all the way through. However, you wouldn't be able to tell by looking at it, but once you get to here, 1, you can see that it's undefined. So just at this single point, it's actually discontinuous. This is a discontinuous function. So how can you identify that this is discontinuous at 1 and only at 1? What's the giveaway in the equation? All right. So it's no coincidence that we have canceled out x minus 1, and that's exactly where there's a point discontinuous right there. Right? There's no value. Right? So f of 1, right, is undefined. It does not exist. So that's the point. So you get that anytime if you do some factoring, you cancel top and bottom, whatever's canceled out is not going to be there, right? Because, of course, if you plug in 1 here, you get divided by 0. So anything causing dividing by 0 is undefined, and you got your problem, right? So be careful on decimals, because this will not show up. You have to have the knowledge of what you're doing to be able to know that that is there. Okay? So that's the 3 types of discontinuous functions that we've looked at so far. A little bit review on how to identify them, and that's information you'll need. But you'll notice that if we do the limit for here, well, what is this getting close to? All right, well, 1, that's getting close to 1. If I look over here, all right, and that's from the left side. And what am I getting close to on the right side? I'm also getting close to 1. So in this case, the limit as x goes to 1 actually equals positive 1. So it would be incorrect to say if it's discontinuous, the limit doesn't exist. Even though for the first 2 we had dne, dne, because they're obviously going in different directions on both of them. But this kind of discontinuous function, they are heading towards the same exact value. Okay? So really, really important to know how to identify them, and if not sure, graph them, but just know those point discontinuities do not show up. Maybe in the future version they'll have it where it automatically puts an open circle there or something, but for now you wouldn't know. Even if you zoom in on it, it doesn't tell you, right? It doesn't show that at all. Just have to know about it. So we're going to use that today to help us find, well, not just where it's discontinuous, like for here, this function was discontinuous at 0. Same thing here, also at 0. This one was discontinuous at 1. We're going to say where it is continuous. So how do you represent all these other values? Right? How do we say, like, oh yeah, all these numbers this way, all those numbers that way, and so on, without including the point that it's actually discontinuous? So that's what you're doing today. And we'll zoom in here, do a few problems. Okay. So can you recall what this will look like? You know what 1 over x looks like this. What happens if you make it minus 3? Okay. Where will the vertical asymptote be? At 3. And how do you know it's going to be at 3? You're just asking yourself, well, what makes the denominator 0? Remember that asymptotes equal dividing by 0. So what value here made this 0 on the bottom? Well, just 0. But what value makes 0 on the bottom here? Oh, 3. 3 minus 3 is 0. So that's the giveaway, again, that you have a vertical asymptote here. And then you can see that it's basically this graph just shifted to the right 3. So it's just going to be the same. 1 over x behavior, right? So you don't need to know, every single type of function, but if you know 1 over x, we should be able to figure out that what 1 over x minus 3 looks like, right? And then if I know the answer to here, and it's, the limit doesn't exist, it's probably going to be the same for here. And you can always look at it and say, oh yeah, left side's still going to negative infinity, right side's still going to positive infinity, right? So these are obviously this single function is going in 2 different places at once, so there will not be a limit at 0 at all. Okay? So we know that there is no limit. We know that x cannot equal 3, right? That makes it divided by 0. But how do I write where it does exist? So there's a couple ways of doing this, right? So basically we're saying, well, if the answer cannot be 3, well, where does the graph actually exist? Right? So we can say, well, it exists to the left of this value, which is 3. So I could say all the x's can be less than 3. Right? Or they can be to the other side, greater than 3. And that's what the answers you're going to be writing down today. It's like not just saying where it does not exist, but saying where it does exist, right? It's kind of like two sides of the same coin of looking at it. So, and there's a couple ways of doing this. I don't know if you guys remember set notation. There's another way of writing this called set notation. They kind of bring it back where it says where you can write everything as like a coordinate, right? Which just means that if I want to say everything less than 3, that means everything from negative, well, I gotta make more room. Everything from negative infinity to 3, and everything from 3 to positive infinity. And we can say or sometimes you see this like just a U between them, which means union. Okay, just means both of them together. We got this or this. So that's another Algebra 2 thing, set notation. So you might write. They might ask you to write it in inequalities or write it in set notation, just so you have both. If it happens to be equal to, if this happened like a different problem had to be equal to, you would have to use a square bracket here. So just so you know, when we have regular, less than, and greater than, it's parentheses, but as soon as they become equal to, you know, it's okay to have one parenthesis and one bracket. They could be two brackets if they're both equal to. With infinity, since you can never be ever actually equal to infinity, right? That would be against the definition of what infinity is. We can never actually reach it. So infinity is always a parenthesis no matter what. So it's the number that might change from a regular parenthesis to a bracket depending on the equals. But these infinities, negative infinities always have the parenthesis. So small little review for set notation. So let's take a look at another similar function like that has restrictions, you know, like there's something about mathematically that makes us troublesome. It's because we're dividing by 0, but you guys also know there's also something troublesome with square root functions, right? And we're dealing and sticking in just the real numbers, not imaginary, so square roots cannot be negative. We can't take the square root of a negative number. So the restrictions on here is not like a dividing by 0, but more of a, well, this number can never be negative, right? So to figure this out, we have to take whatever's inside the radicand and say, well, where is that equal to 0, right? This can never, it can equal 0, sorry. Okay, where is it negative? So it can be 0 or bigger, it just can't be negative. So I have to solve this solve this quadratic equation and find out where is this thing equal to 0. All right. So as usual, try when you get polynomials, especially quadratics, try factoring. So what does it factor to? Well, it multiplies to 4. Or negative 4 adds to negative 3. So it looks like we'll get a 4 and a 1. One of them is negative, one is positive. I need to get negative 3, so it's going to be negative 4 plus 1 gives me negative 3. Negative 4 times 1 gives me negative 4. Alright, so I have two possible places where this could equal 0. Alright, so at 4 and at negative 1. So just for kicks, let's take a look at the graph, because chances are we probably can't just look at this and know exactly what it looks like. So let's just take a look at the graph. I can always SQRT minus 3x minus 4. There we go. Alright, so it looks like, where'd it go? Oh, there it is. Yeah, so it looks like, oh, there's more of it right there. Here's what it looks like. So it looks like the graph exists starting at negative 1 and going to the left, and starting at 4 and going to the right. So slightly different, right? We don't have these asymptotes really, but the question is, how can you figure that out without actually having decimals open? Right, that's the big question. So we have three different ranges. We have the range that's to the left of -1. We have this middle part, and we have this part to the right. And we just need to know, like, well, where is a negative, where is undefined? And it appears, there's nothing between here and here. That -1 and 4, there's nothing between them. But how can we figure that out without actually having a graph? So what we do is we just do an old-fashioned trial and error and just kind of test some values. Once we have our numbers here, we can just test them. All right, so say I got my number line, and we got our two numbers to work with here. We know at -1 that something happens, and at 4 something happens. So we can just test some numbers in between here. So if I can test like a number, let's say 2, or -2, right? And I just plug it into here and see, do I get a positive or negative number? If I get a positive number, then it's part of the answer. So if I plug in -2, right, I'm just plugging it into -2 into both of these, right? You could plug it into the original function as well. This is the factored one is usually a little bit easier to plug it into, but whatever works. So -2 minus 4 and -2 plus 1, and we get -6 times what? -1, which is +6, right? And the main part there is that's positive. So that's how I know starting at -1 and everything to the left is actually part of the function. So I just proved by plugging something in, yes, it does start here and the graph continues this way. This isn't like a place where we're getting negative answers. So I can confirm that without the actual use of the graph. So far, because of that, I know my x can be less than or equal to -1. I know that much. Now, I could do the same thing and just plug in, let's say, 6 on this side. And if I do that, we have 6 minus 4 and 6 plus 1. Number is not important. The fact that we get a positive number lets me know the same thing, that x can be 4 or bigger, greater than or equal to 4. So what happens, and that just confirmed this, right? Without using the graph, that means I know it starts at 4 and the graph continues going to the right. How can I confirm that there's nothing in the middle here, that that's completely empty? So test yet one more number in the middle. And of course, if you ever have the opportunity to use 0 as your testing number, that's usually the easiest. So I'm going to use 0, plug in 0, right, and see what you get. So we get a 0 minus 4 times 0 plus 1. And you'll notice that 0 minus 4 is -4. 0 plus 1 is just 1. And we get a negative number. And again, we can't take the square root of a negative, so that's why that's not part of the domain. That's not part of the answer. It does not exist there. So for now, use decimals. If you're not sure, if your answer is correct or not, you could always graph it and just take a look at it and see, like, okay, I know my answers ahead of time should be, x is less than -1, or less than or equal to -1, and x is positive, greater than equal to +4, and I shouldn't have anything in the middle. And now let me go and find a analytical, equation-based way of figuring that out. So that's what we just did. So use decimals as a tool at some point, but at some point you're going to say, okay, I need to do it without the knowledge of the graph. And of course, write it multiple ways. So here we have negative infinity to -1, or 4 to positive infinity. And actually those are incorrect because these have equals on them. Both of them, it can be -1, so I need to put a bracket there. Same thing, it can be +4, so bracket. Alright, you guys go and try 1. Do the same thing, kind of factor it down. You'll get 2 values, create the number line, and test the numbers at all 3 parts on the left, in the middle, and the right. And then we can come up with exactly what our real domain is here. Where does it really exist? So go and give that a shot, help each other out. You can use decimals and everything. So many instantly went and factored, which is a great idea. Something's factorable. Usually we can get more information out of it when it is factored. So we got x, and what was it, -3 and -4. But nothing really canceled out, but that does reveal where the asymptotes are, right? So we do know from both of these, well, where does x minus 3 equal 0? Of course, that's at 3. And where does x minus 4 equal 0? Right, x equals 4. So we know we're going to have some asymptotes there, right? So, but what's happening in the middle? So you go through there and say, well, 3 and 4. And we can verify without a graph, but just for kicks, right, we can go over here and graph it just to get a sneak peek. Why not? Okay. And this appears, zoom in, zoom in. Type this in right? Double check. Ah, plus 12. That's why. There we go. Plus 12. Okay, there we go. This does appear to have a gap. Yeah, it looks like we have some vertical asymptotes. Just as expected, this is approaching 3 from the left. Never will quite get there. This is approaching 4 from the right. We'll never quite get there. I'll just get closer and closer to 4. Right? Has a limit as x goes to 4 is infinity on both sides. And there's nothing going on in the middle. Right? So when we do our checking, we expect, once again, to have something on the left, something in the right, but nothing in the middle. It appears completely empty. So just go ahead and verify that. So you can pick any number. Like I could pick anything that's less than 3 to verify that 3. Anything less than 3. So once again, when you have the opportunity, use 0 as one of your points because it's the easiest thing to plug in. And you can plug it into the factored version if you want. It's a little bit easier. So it would be 0 plus 1 over 0 minus 3 times 0 minus 4, right? So it's a little more work to plug it in, but we'll end up with 1/12. So that's totally fine. So I know x is going to be less than 3, right? Not equal to 3 because it's vertical asymptote, right? Or I could say negative infinity to 3. And plug in a number to the right. Let's say 5 or 6 or 10, whatever you want. But if I plug in, let's say 6, I'll get 7 over 6 minus 3 is 3 times negative 1. And I just need to have some number, right? As long as I'm not getting a 0 here, I'm okay. So then x can be greater than or equal to 4. From 4 all the way to infinity. Another way of saying that. Not greater than equal to. Why did I say that? Asymptotes at 4. So just greater than, strictly greater than 4. So from 4 to infinity. There we go. And just for kicks, go ahead and check something in the middle here. What's between 3 and 4? You can choose the middle, like 3.5. And you can check that. So 3.5 plus 1 is 4.5. And I plug in 3.5 minus 3 is going to be 0.5. 3.5 minus 4 is going to be 1.5. So I get a positive number here. I get a full number here. That means there's an answer. There should be a graph for this. Interesting. Go back here. So if you zoom out a little bit, it does exist. So I was getting ready to say, no, there's no answer between 3 and 4. And when I first graphed it, if I'm at standard zoom that Desmos automatically puts you at, it might appear that. This is why we go through this exercise of actually checking it. Because sometimes our tools are not completely reliable. So we go through them and say, you know what? No, it exists here as well between 3 and 4. So we also have answers between 3 and 4. That's part of the domain. Right, so it would be very tempting just to say, well, it's probably just like the last one where, you know, it worked on the left and right but not the middle, and, you know, these things are all the same, and it's the middle that's never going to work. Not necessarily, right? This is a square root function where you have a limitation of not having negatives in the square root. This is a rational function, which is, only has limitations about dividing by 0. So, right? So I went through this exercise of actually showing it without the zoom out and then with, so you can be aware of that, yes, we can use tools, but sometimes they don't give us the full truth. It didn't give us the point discontinuity earlier, right? Because the Desmos did not show us this early on, right? So we're kind of aware of, all right, there's some limitations with Desmos. And then for the second time over here. So we use it with caution, and then we always check our work just in case. So on this particular problem, we could say, yeah, x is less than 3, x can be between 3 and 4, and x will be 4. That's just the same as saying x cannot be 3 or 4. Right? It's the same thing. It could be anything. There's, any value that actually exists except for at 3 and at 4. So the limit does not exist at those values. All right. So there's one more type of problem. These are a little bit faster. If you add the examples, you can reverse engineer it. So think about what we're about to do next is just doing the reverse. So what if I went the other way? Based upon this problem where x cannot be 3 and 4, could you work backwards if I gave you this information to come up with this equation? All right, so basically you could start here, not jump straight there, but, well, x can't be 3 or 4. That means you're dividing by 0 at 3 and 4. So that's how you get x minus 3, x minus 4, because a 3 would make this divided by 0, a 4 would make that divided by 0. So let's change it up a little bit. What if I said the values were -2 and +1? What would you put to start off with? Right. So we'd have to recognize that this is created by a vertical asymptote, which means you're dividing by 0. So 2 numbers translates to 2 parentheses. And what expressions would you choose so that you got 0 when you plugged in that value? All right. So that's how you can come up with what is it, -2? Is that correct? No. So I plug in -2, I got -4. So I needed to plug in -2 and get a 0. So get the signs correct. If I plug +2, I plug in -2, now I'm dividing by 0. Same thing over here. I need to get a 0 when I plug in 1. That's why it can't equal 1, because it gives me a 0 divided by 0. So I get there. And what goes on top? All right, here I put x plus 1, but what if I just had like x? Right? Well, it still has the same vertical asymptotes. What if I had like 2x plus 3? Right? I still have the same situation. The graph bends and moves a little bit differently, but you'll notice how the numerator doesn't really have a whole lot of effect on where it's, those vertical asymptotes are. I could put this to be pretty much anything that's linear, right? Or just a number, 5 or 9 or pi, whatever. It still has the exact same asymptotes, right? So the top doesn't really change, what's going on here. So you could put just about anything. If you want to just mirror the example that has x plus 1, right? You could put it x plus 1. As long as it doesn't cancel one of these on the bottom, you're okay. So I could say the top could be anything except for an x plus 2 and an x minus 1, right? Because if it canceled out, then it'd be like that point discontinuity. It wouldn't be a asymptote anymore. All right, so that's one possible thing, and we'll give it a name. All right, just like that. All right, I'll let you guys try this one. Just do something with point discontinuity at 4. So use this example, but you want, instead of having it occur at 1, you want to have it occur at 4. So just reverse engineer it, and lots of correct answers. Just choose the one that's more simple and maybe based upon the example, just for simplicity's sake. All right, and your homework is right down there, 1 through 7, 11 through 20. All right, it's going to take you more than 25 minutes, half hour max, possibly. Give you a second. If you just take the one from up here and adjust it to x minus 4 instead of x minus 1, you'll get the point discontinuity at 4 instead of 1. Okay? All right, that's it. Cool. All right, you're all set. Good job.